Welcome back. We're going to talk now about how to alkylate ketones. Now, one interesting and important thing to consider with ketones is that the carbonyl does reside somewhere in the middle of a chain, and there's no guarantee that that chain will be symmetrical. So what that basically entails is that you can have different types of enolates, and as a result of that, different types of products. So consider, for example, the ketone that I highlighted right here. So 2-pentanone. You have two types of alpha hydrogens. The one on the left here in red, which is present on a secondary carbon. And then you have the proton in blue shown here on the right side, which is present on a methyl carbon, primary if we want to be technical. All right, so the idea right here is that depending on what kind of base you end up utilizing, you can facilitate the formation of one enolate over the other. So for instance, if we use a relatively small but strong base like lithium amide in the presence of excess ketone, and you keep this at relatively high temperatures, and I'm definitely using the word relative very much in accord right here, because room temperature is not a hot temperature, but it is compared to negative 78 degrees Celsius temperature used for making your lithium enolate, as mentioned in a previous video. What you basically end up favoring is the formation of the enolate, in which the alkene portion of the enolate ends up being the most substituted possible alkene that you can form in the molecule. And this only happens if you deprotonate the alpha proton that is present on the most sterically encumbered or the most sterically hindered site. We call this the thermodynamic intermediate because it's forming the more stable alkene out of the two options. So going ahead and forming that stable enolate, which by having higher temperature, and excess ketone allows for full equilibration to favor the formation of the more stable enolate. You can then react that with an alkyl halide, and that alkyl halide can undergo an SN2 reaction with the enolate to alkylate the more substituted position. And that will be your thermodynamic product. Now, if it is the case, however, that what you actually want is to deprotonate and ultimately alkylate the site that is less sterically encumbered, then the way you go about facilitating the deprotonation of this blue proton is by using a very bulky base. So lithium hexamethylate salicide will do the trick. Lithium cyclohexyl isopropyl amide will also do the trick. You do this, however, at low temperature. And now you have two really effects right here. So I told you that, yes, you stabilize the enolate at that low temperature, but you also have a dual effect happening here. You keep the enolate kind of stable, without it, kind of going crazy on you and remaining relatively stable, but also by keeping the temperature low as the deprotonation event happens, you make it very difficult for the lithium amide to, run away from the more accessible proton. And so you make it less likely that diffusion will occur onto the opposite side and deprotonation happens there. And of course, the bulky sides, the bulky R groups on the nitrogen will also prevent access to the red proton because there's just not enough space available. So this is the kinetic intermediate automatically. And the enolate form, it's the least sterically encumbered, but also it is the least substituted alkene. So when you form that under low temperature, you add your lithium alkyl or your alkyl group with, a proper leaving group, and you let this reaction go. And technically you warm it up. But here, instead of equilibrating from the least substituted enolate to the more substituted enolate, the least substituted enolate already sees a really good electrophile present in the solution, and so goes after it. And assuming that you didn't use excess ketone, then this will definitely be ensured that doesn't equilibrate as you warm up the solution. So you end up making your alkylated product on the most available position, the least sterically encumbered position. So, something to keep in mind with ketones. All right, so as far as bases go, so one thing that I should kind of highlight is that you have options as to what kind of bases you could use. They're going to be all nitrogen based, but I just want to make sure that we know of the bunch. So there is lithium hexamethyl disilazide, which I mentioned already, and that's basically the amide in which you have connection to two silyl groups, two trimethyl silyl groups specifically. This is sometimes abbreviated as LHMDS. Personally, I don't tend to use that acronym as much. I either just spell out how it's called, the proper name, or I simply, draw out the molecule as, lithium N with two TMSs. Now, two things that I want to say about it is that, yeah, this material is definitely available commercially. Pretty much any chemical supplier will offer this, and they offer in various forms. It could be the pure solid, or it could be a solution, which then you can transfer, using either needles or syringes to go from the silk container into your flask where you're trying to do your reaction, or you could use what you can see here is a double-headed needle. And the way that this kind of works out is that you purge the the bottle that has your reagent with some air, or in this case probably pure nitrogen, to semi-pressurize the bottle right here, and then the pressure allows the liquid to exit out through one of the heads of the needle that you see right here into your other flask, and then that flask is also connected to the same apparatus so that it has technically an opening, so you are kicking out air, letting the solution of your base enter the flask. It's a pretty convenient method to do chemistry to avoid introducing moisture or air in the process. Another big base that you could use is lithium tetramethyl piperidide, which looks as follows. Basically, you have a cyclic amide in this case, and you have the four methyl groups at the ortho positions in respect to that nitrogen. This is the conjugate base of piperidine, so that's where the name derives for. If you take the acronym, the way it basically spells out for the big letters right here, this is also known as LTMP. And just like lithium hexamethyl disilazide, this can be offered as a pure solid or even a solution. Another big base to be aware of is lithium isopropyl cyclohexyl amide. That, technically speaking, that's not the correct name. It should be lithium cyclohexyl isopropyl amide, but by kind of rearranging the alphabetical order, you can call this Lika, which I think is a pretty hilarious name for it, but so some people refer to it. And yes, same deal with this. This can be part of a solution. It could be the pure thing, but these are big enough bases that yes, you will facilitate the deprotonation at the least substituted site on the ketone. Okay, so with that, we only have two more things to talk about, and this happened to be kind of short, so we're going to include them in this video. We're going to talk about how we go about alkylating esters. So the best way to do this is to basically have your ester, in your flask. You cool this down, and then you introduce your base under low temperature. And what this will do for you, especially if the base is big, is it will attack the alpha position of your ester. It will not attack the carbonyl for two reasons. One, the base that we're using is big, and so access to the carbonyl site is not as reasonable to assume for that nitrogen. And the fact that you're doing it under cold temperatures means that yes, you really don't have a lot of room for any kinetic shenanigans going on, molecularly speaking. So you only attack the alpha protons. And basically when you mix this, you will deprotonate the alpha protons and form the lithium enolate version of that ester. Then you introduce your alkyl halide and you let the reaction warm up to room temperature. So here we go. We introduce the alkyl halide and then we just let it warm up to room temperature, either by removing the flask from the cold well, or just letting it cool down, or excuse me, cool up, warm up over time. But that will, in essence, just allow the alkylation to happen like it happened with the ketones, like it happened with the aldehyde. So there's really no difference here. The only really difference is that we are dealing now with the ester enolate, that's the intermediate. And aside from that, the conditions are virtually the same as what we did for the ketones. All right, so that's basically it. And then for the nitriles, you can get away with using a small base like sodium hydride. It has about the same power uh, as the deprotonated amines, so it does the same trick. So you can deprotonate the alpha position of the nitrile. In the process, you form H2, right? That basically just comes out of the flask, and you produce this enolate derivative, which you can react automatically with an alkyl halide, of proper SN2 reactivity. So in the process, the lone pair of the nitrogen will come back to carbon. The carbon-carbon double bond that we have here will attack the electrophilic position of the substrate, thus lengthening the size of that nitrile. And this could very well be the end point of your reaction, but you also have the option, after you elongate the alkyl chain, to basically convert the nitrile functional group into a carboxylic acid just by treatment with aqueous as acidic media under heating. So something to keep in mind for future synthesis. And with that, we basically are done with this chapter. So we have talked plenty about the chemistry of enolates, but as you will find out in the next lecture series, there's actually a lot more to be said about it. So stay tuned. But for now, this is it for this lecture. So I'll catch you up on the next lecture series. Bye bye.